All right, so today we're going to start off with looking at the first part of graphing rational functions. So what we're going to focus on today is the domain, our in behavior, and our vertical and horizontal asymptotes. So some of the key features of the graph. So rational functions are our rational expressions we are looking at, but just set equal to y. Okay. So the domain of a rational function is the set of all real numbers except the x values that make the denominator 0. So this is similar to what we've seen before. We want to make sure that our denominator is factored and then determine what x cannot equal. So if we look at this first example, f of x equals x squared minus 9 divided by x minus 3. Because of that x minus 3, we have x minus 3 cannot equal 0, which tells us x cannot equal 3. So our domain, the way you're going to see it in your homework, is it's the set of all real numbers x such that x does not equal 3. So that's your set builder notation for domain. All right, looking at b, we have x divided by x squared minus 9. So if we factor that denominator, this becomes x plus 3, x minus 3. And if we set each of those not equal to 0, we get x cannot equal negative 3 and x cannot equal positive 3. So our domain is the values of x such that x does not equal plus or minus 3. All right, looking at the second, or this last one, x squared plus 9. Well, we can't factor that. So let's go ahead and try setting it not equal to 0. So if we subtract, we get x squared cannot equal negative 9. And if we take the square root, we get plus or minus 3i because of that negative. We don't care about our complex numbers. So here, our domain is all real numbers. Okay. All right, so we're going to kind of jump around the notes. We're going to skip this reciprocal function and talk about what the graph looks like here in a bit, or in the next couple days. Here, let's look at this in behavior. Okay, so this is some new notation. It's called arrow notation. The things to remember, so plus sign means that we're approaching from the right. Negative sign means we're approaching from the left. And then as x approaches infinity, and then x approaches negative infinity, that's talking about our in behavior to the left and to the right. Okay. So here you're given one of our basic rational functions that we're going to talk more in detail about later this week. F of x equals 1 over x squared. So the graph of this even function with y-axis symmetry has positive function values as shown below. So from this, if you're given the graph of the rational function, complete each statement. So looking at A, we have as x approaches 0 from the left. Okay, so I'm going to use our graph. So as x approaches 0 from the left, we want to know where is y. So as we draw that, as we get closer to 0, our y is going to continue going up, and that would be going up to positive infinity. Okay, so erase that guy. So now as x approaches 0 from the right, because of that plus sign, so I'm going to take our line. As we get towards 0 from the right side of the graph, it's going to keep going up towards infinity. So it's just kind of asking you, well, where is y at? What's happening to our y value? All right, last two. So as x approaches negative infinity. So negative infinity, remember, is over here on the left. And as our graph approaches negative infinity, what's our y value? We're getting really close to 0. Okay. And as x approaches positive infinity, which remember would be over here on the right, our graph is getting closer and closer to 0. Okay. So each of those lines, okay, this y-axis and the x-axis are both examples of asymptotes, one being vertical and one being horizontal. And that's one of the things that we use with this approaching from the left and the right. Okay, so let's look at those rules. Okay, so looking at vertical asymptotes. A vertical asymptote appears whenever your domain does not exist. Okay, so whenever x is in your denominator, we need to figure out what x value would make the denominator 0. That represents a vertical asymptote. There's one time that instead of an asymptote, it becomes a hole, and we're going to look at that here in a second. So to find the vertical asymptotes, you're going to always start off with factoring. So I'm going to rewrite this first one, x divided by x squared minus 9, as x over x plus 3 times x minus 3. Okay. You want to check to see, does anything cancel from top to bottom? Nothing does. So for our vertical asymptote, I'm going to always abbreviate that VA. We're going to set each of these equal to 0. So x equals -3 and x equals +3. And those are the equations of the lines of your vertical asymptotes. All right. And we're going to talk about how to graph those tomorrow. All right, so looking at B, x plus 3 divided by x squared plus 9. We talked earlier about how x squared plus 9, if we solve for that, we get an imaginary number. So that means that there are no vertical asymptotes. Okay, and that's because the domain is all real numbers. Okay. All right, now let's look at C. So we know we can factor this. So we have x plus 3 on the top over x plus 3 times x minus 3. So if we simplify this x plus 3 expression cancels, and we're left with 1 over x minus 3. So for our vertical asymptote, we take that denominator, x minus 3, and set it equal to 0. And that tells us that x equals 3. But we know from the domain that x cannot equal -3. Plus or minus 3. So we need to figure out what happens when x equals -3. Well, when x equals -3, the graph does not exist, or DNE. So there is a hole when x equals -3. Okay. And we're going to talk about how to graph something like that in class together. Okay. So we're going to save this for in class. All right, so after talking about vertical asymptotes, let's talk about horizontal. So I gave you your book's definition. Okay. Horizontal lines create our asymptotes, and they're completely based off the degrees. You can find the horizontal asymptotes by actually doing long division or synthetic division, depending on your polynomials. But we're going to use the degree rules to help. So you want to focus here. The degree of the numerator is n, and the degree of the denominator is m. If you want to change that to be like a lowercase d, so it's easier to keep track of, I'm okay with that. Okay, so if n is less than d, the x-axis, or y equals 0, is our horizontal asymptote. Our second one, if n equals d, We look at the leading coefficients, and that becomes our y equals horizontal asymptote. And if n is greater than d, the graph of f has no horizontal asymptote. So, looking at these three examples, we're going to look at, first off, just our degree of our numerator and the degree of our denominator. So, I'm going to say the degree of n equals, so the degree of our numerator, looking at our exponents, would be 1. And then the degree of our denominator, d, would be 2. Since 1 is less than 2, our horizontal asymptote, which I'm going to abbreviate HA, is simply y equals 0. That's what the rule says, so we're done. All right, looking at B, so same thing. We're looking at the degree of our numerator, which is 2, and the degree of our denominator, which is also 2. Since these are equal, our horizontal asymptote, we look at our leading coefficients. So our leading coefficient of our numerator is 4, divided by the leading coefficient of our denominator is 2. And 4 divided by 2 gives us the asymptote y equals 2. And looking at C, the degree of our numerator equals 3. The degree of our denominator equals 2. And since the numerator is greater than the denominator, there are no horizontal asymptotes. Okay. Instead, we're going to talk in the next couple of days, we're going to be checking for a slant asymptote. Okay. All right, and we will go over a couple of those things tomorrow in class.